Good evening, everyone. Welcome to the public lecture hosted by KIPAC, the Kavli Institute for Particle Astrophysics and Cosmology. My name is Sinan Du. I am the Outreach Engagement Manager at KIPAC, and I will also be your main host tonight. Thank you all for joining us either in person or online, as we are essentially wrapping up this year's programming, and this is our very last event of 2024. Some of you may have heard of the word high energy astrophysics. It is a subfield that typically do not get covered much in public events, except for, when there are buzzwords such as black holes or neutron stars. So there hasn't really been a lot of KIPAC public lectures on this topic as well, at least not in the past few years. And there has been so many new discoveries and developments. So we're just very excited to share with you tonight on a particular topic, the fast radio bursts, which is a very new and rapidly evolving field. So before we start, I would like to give a big shout out to the entire team who is supporting this event behind the scenes. So you may have already met the front desk staff. We also have our tech team here, and we also have Leon, who is managing the live stream for the KIPAC page. We also have chat moderators who are subject matter experts on this very specific topic, who will help answer questions. And I will let them quickly introduce themselves. So first we have Jack.
Hi, everyone. I'm Jack. I'm a grad student working on high energy astrophysics here at Stanford.
Great. Next, we have Josephine.
Hello, I'm Josephine. I'm also a grad student, and I also work in high energy astrophysics.
Wonderful. And last but not least, we have Andrew.
Hi, everyone. I'm Andrew. I'm also a graduate student here at Stanford, studying same thing as Jack and Josephine.
Wonderful. So for those of you who are joining us online, you're more than welcome to put your questions or any kind of discussion topics in the live chat. Most of the questions will be answered directly by our chat moderators, and the remaining field will be saved for Navin to answer during the Q&A. And for all of you who are joining us in person today, you can save your questions until the very end during the Q&A. And of course, even after this event, you have plenty of time to also chat with Navin one-on-one if you prefer to. So now it is my great pleasure to introduce tonight's speaker, Dr. Navin Sridhar. Navin is a postdoc researcher here at KIPAC Stanford who studies high energy astrophysics. One cool aspect, at least personally I found Navin's work, is that he uses a lot of high energy cosmic events, even including very violent explosions, to study physics under extreme conditions that cannot be replicated in any labs on Earth. Navin's work is mostly focused on the theory side. So he does a lot of analytical modeling, doing computer simulations, but occasionally he also does direct observations of those high energy cosmic events. So Navin got his bachelor's and master's degree from the Indian Institute of Science Education and Research, BAPEL, and he received his PhD in astrophysics from Columbia University before joining Stanford. So without further ado, let's welcome Navin.
Right. Thanks so much, Shinan, for organizing this and for the kind introduction. Let me share my screen quickly. Okay. All right. I guess it's working. Okay, yeah. So the phenomenon of fast radio bursts that we are going to discuss today has attracted so much press over the last decade or so. And yeah, this has truly been an unexpected phenomenon. We have never seen a phenomenon like fast radio burst from any natural source, any naturally occurring cosmic events. Right now, sorry? It's echoing, okay. So right now, as we speak, our Earth is being bombarded by these fast radio bursts. And we still do not know where they're coming from. We still do not know what's producing them. And these emissions could hold the key to understanding physics in some of the most extreme regimes, and also to understand the composition of the universe, and also the structure of the universe and its expansion and so on. So yeah, this is not fast radio bursts. In case you're thinking it's an exploding radio. So before understanding fast radio bursts, we have to understand the electromagnetic spectrum. The colors, as we see, range from red to violet, the ones that you see in the rainbow, red being the longer wavelength ones with lower energy, and violet being the shorter wavelength ones with relatively higher energy. And the entire electromagnetic spectrum is much, much broader, wider than what we can actually see with our eyes. Beyond the red wavelengths, you have what are called infrared waves, which are even longer in wavelength and lower in energy. And then there's radio waves, which are the wavelengths can be meters to even kilometers long and extremely lower energy. Oops. Yeah. And beyond the blue light, we have ultraviolet rays, which we know that the sun emits, for example, but we cannot see ultraviolet rays. And then you have X-rays and gamma rays, which are some of the most energetic form of electromagnetic waves. These are essentially different colors, just that we cannot see them. You can imagine this as, you can imagine a piano, and just imagine that these two keys are the ones that you can listen to, and the entire range of piano is blocked off from you being able to listen. That's the analogy that you can draw for electromagnetic spectrum. The universe, however, emits light in the entire band of electromagnetic spectrum. It doesn't care whether we can see it or not. The atmosphere, thankfully, blocks most of the electromagnetic spectrum from reaching us, and that's why life as we know it is currently is even possible on Earth. It blocks ultraviolet X-rays and gamma rays, and the atmosphere also blocks a lot of infrared rays. So astronomers place telescopes at different regions in the atmosphere to study the emission in different bands. In order to study X-rays coming from our universe, astronomers use satellite-based X-ray telescopes. And so for gamma rays, and also for some bands of infrared. But thankfully, we don't need to put all the telescopes in space, because the atmosphere allows optical radiation from red to blue to enter the Earth's surface. So we can have regular telescopes. And also, we can have telescopes on Earth to observe radio waves. So these are radio telescopes. So what does the sky look like if we had radio eyes? So what I've shown here is a composite image of what the sky would look like if we had radio eyes. The dots that you see here, these are not just stars. These are entire galaxies that are sitting at billions of light years away. And this the black region that you see here is the National Radio Astronomy Observatory site in Green Bank, West Virginia, that has a huge array of telescopes. And these diffused regions that you see here in radio sky are what are called supernova remnants. I will quickly discuss about supernova remnants in the upcoming slides. So the cosmic radio signals that we receive on Earth are a billion times fainter than what our cell phone emits. So in order to study these cosmic radio signals, we have to build huge telescopes, huge collecting area, something like this that you see here in the slide. So this is the Green Bank telescope that I shared in the previous slide. And in American units, this is 1 football length in diameter. Yeah, that's an example of a radio telescope. This can actually turn and point at different regions of the sky and collect radio information. So now that we have some sense of what radio astronomy is and so on, let's travel 55 years back in time to a moment that actually led to the eventual discovery of fast radio bursts, among other discoveries. November 1967. So this is Jocelyn Bell. She was a PhD student at Cambridge University, and she's standing in front of what looks like a vineyard, but it's actually a radio telescope, a primitive form of radio telescope. It's all basically antennas strung together. And in 1967, Jocelyn Bell and her then advisor, Tony Hewish, they were trying to study the twinkling of star-like objects in radio sky. We see stars twinkling in optical band, and that's primarily because of the turbulence in the atmosphere through which the stellar light has to pass through. But these radio twinkles that they were looking for are mostly due to the radio colored light passing through interstellar medium, far away interstellar medium. That's what they were studying. And while they were studying this, they were observing strange signals in their data, especially when the telescope was pointing at a particular patch of the sky every day. So this vineyard is the telescope, right? So when the Earth is rotating, it observes certain patches of the sky, and at certain patch every day they saw some strange signal. So this was a signal that they called it CP1919. CP stood for Cambridge Pulsar. And when they zoomed in, they found that there were even finer structures within this graph, some little pulsations in the radio light curve. And these pulsations occurred once every second. It acted like a very precise clock. It was then named as pulsating radio sources, hence pulsars. So this discovery started the era of transient radio astronomy, and eventually led to a Nobel Prize. But unfortunately, Jocelyn was not awarded the Nobel Prize. Only her advisors got the Nobel Prize. Very sad, but yeah. So what's producing these pulsars? In 1968, a pulsar was observed from this Crab Nebula. And the pulses from that nebula was seen to repeat about 30 times a second, 30 times more frequent than the pulsar that Jocelyn discovered. And interestingly, this pulsar was associated with the presence of what's called a supernova remnant. So this GIF that you see here is a star, it's a massive star exploding, and once it explodes, it leaves material behind. That's called supernova remnant. And we had an idea even in 1960s that such exploding stars could give rise to what are called neutron stars. The core of the massive star would leave a neutron star behind. What are these neutron stars? These are, like I said, the stellar remnants, the collapsed core of massive stars. And these are some of the densest material known in the universe. To give an idea, you just have to take entire Mount Everest, collapse it, and then put it in a tablespoon. That's how dense a neutron star material would be. And yeah, that's a typical size of a neutron star. It's very small. It's just 15 miles in diameter, somewhere from, say, Redwood City to Hayward. That's how big the entire neutron star is. And this is also one of the strongest magnets in the universe. It's about 10 billion times stronger than the MRI magnets that people use in hospitals. The idea behind pulsars is that these neutron stars, these are extremely quickly spinning structures, and you can have a lighthouse kind of an effect. Neutron stars emit radio pulses in one direction, and when it's passing along a line of sight, you see a pulse, and then it repeats again and again. That's the idea behind a pulsar. So all these pulsars that were discovered were from within our galaxy. So astronomers, radio astronomers, they went looking for pulsars from outside our galaxy. So in 2007, Duncan Lorimer and his students in West Virginia University, they started looking for pulsars from these Magellanic clouds. That is an artistic image of the Milky Way galaxy, and Milky Way has these two little clouds next to it. These are not exactly part of our Milky Way, but these are satellites of some sort. And they were looking for pulsars from these nearest non-Milky Way sources. And while they were searching for this extragalactic pulsar, they found an extremely bright flash in an archival data from 2001. And the location of this flash in the sky was about 3 degrees away from the small Magellanic clouds. This is small Magellanic cloud in optical band, like what we can see. And this is how it looks like in radio. And the pulse, the strong pulse, was seen somewhere over here. So these are the 13 pixels of a radio camera. Our phone has thousands of pixels. The radio camera that they operated with had 13 pixels. And they found this bright pulse coming from this region about 3 degrees away. And they also observed a very large dispersion measure, that is a sweep in the frequency temporal structure. What do we mean by this dispersion measure? Let's take a pulsar. It's emitting radio waves. The high frequency waves are here and the low frequency waves are here. It's going to intercept some matter in the universe. And this matter slows down the low frequency waves, and the high frequency waves are not slowed down. Let me play this again. So this is what is happening. So the pulsar is emitting color radio signals in a colorful radio band, and the high frequency waves are not slowed down by the intervening electrons and plasma, whereas the low frequency waves are slowed down. So eventually you end up you end up seeing high frequency waves arriving earlier and the low frequency wave arriving later. Let's take the piano analogy again. So you have a cosmic pianist, and that pianist is going to play a C major, C, E, G notes. But what you hear is G, E, C notes, high frequency, and then it goes to lower frequency. That's essentially the concept of dispersion measure. And the time delay between high frequency and low frequency arrivals can be used to infer the distance that this radio pulse has traveled to reach Earth. So using this concept of dispersion measure, radio astronomers put a distance as 3 billion light years to this radio pulse. And they also found the brightness to be about 1 trillion times larger than the typical pulsar's brightness. And thus the first FRB was discovered, and that's this FRB was called FRB 010724 because 2001 July 20, that's when it was discovered. That's when it actually appeared in the data. So it's so bright that it confounded all the astrophysicists, and we only had an idea that it has to be a coherent emission. What I mean by coherent emission is this. So if a sun-like star were to emit FRBs, then it has to be heated by maybe trillion times more than what its current temperature is to produce an FRB-like emission. That's just physically not possible. And the light that sun emits and most of the incandescent bulbs emit are incoherent lights, incoherent light. Whereas a laser produces what's called a coherent light. So essentially, we just needed a space laser to operate to produce an FRB-like emission. We just didn't know which sources could produce such space lasers or what could be the specific emission mechanisms. So once this FRB was discovered in 2007, for the next 4 or 5 years, astronomers from different parts of the world also kept searching for these FRBs. And dozens of signals were found that resemble FRBs at the Parkes Radio Observatory in Australia. So this is one such pulses. So this is a frequency time structure that you saw earlier. You see the dispersion here, but you see some blobs arriving at different times. Quite a strange pattern. And interestingly, these pulses were seen more frequently during midday. So this is a histogram of when the astronomers saw these radio pulses. It peaked somewhere between 12 to 1 p.m. Quite strange, and it was perplexing. And it was found that it's not really an astronomical event, but people using the microwave ovens in the cafeteria during lunchtime, they opened the doors of the microwave oven before the cycle actually finished, and that's what gave rise to these FRB lookalikes, and some papers were even written about that. These pulses were called peritons, which was named after the mythical winged stag that cast a shadow of a man from the Book of Imaginary Beings. And in 2012, as radio astronomers found this FRB 121102, 2012, November 2nd. It was just a normal FRB, normal burst. And 3 years later, 10 more bursts were discovered from the same point in the sky with the same dispersion measure. If you remember, I said dispersion measure gives, it's essentially a proxy for the distance, right? So same distance, same location in the sky, which just tells you that a single source is now emitting multiple FRBs. So these are not one-off events anymore. So many theories that were proposed originally, for example, bombarding neutron stars or neutron star black hole mergers or exploding stars and whatnot, they all were immediately ruled out as a source of FRB 121102, because these cataclysmic events, they just happen once and you cannot produce multiple FRBs. And this FRB source is still on 12 years from its discovery. We still see pulse from it. So it ruled out all these cataclysmic channels for FRB production. Maybe some flaring, persistent compact objects could produce FRBs. What are compact objects? These are neutron stars and black holes. Maybe they produce some flares occasionally, and that's what's producing FRBs. We don't know. And the discovery of repeating FRBs, there was a watershed moment in FRB science, because FRBs can now be localized, can be pinpointed to their host galaxies. They're not coming from our galaxy, we know that. They're coming from some other outer galaxies. We can now pinpoint them to the host galaxies. I'll tell you how and why. So until 2017, the goal of FRB astronomers, FRB doing astronomers, was to use large single-dish radio telescopes that are extremely sensitive with wide field of view in the sky to observe more and more FRBs. They wanted to collect more sample. But now that we know a single FRB repeats again and again, we can point our telescope at the same location with much more sensitive and different facilities. And that's what happened after 2017. Radio astronomers used something called interferometers. So it's an array of radio telescopes, not just one, but a bunch of radio telescopes acting together as one radio telescope. That's the interferometry, technique of interferometry. And this arrangement gives extremely good spatial resolution. And the goal was then to pinpoint the location, the host galaxies of FRBs. And yeah, so for example, this is the same exact technique that astronomers used to make a picture, an image of the black hole at the center of our galaxy that you may have all seen sometime last couple of years. And these telescopes were spread across different countries and effectively using the entire Earth as a radio telescope. Yeah, media always has a way to give their headlines. Astronomy's secret weapon in the resolution wars, interferometry. But anyway, this technique allows radio astronomers to resolve and see a penny on moon's surface. That's how powerful these interferometers are. So now that we can pinpoint the galaxies that emit FRBs, which galaxies emit FRBs? Is there anything special about those galaxies? FRB 121102, the first repeater that we saw, came from a galaxy with very low metal content, which was very small, a dwarf galaxy, but a star-forming galaxy. It was forming stars very, very rapidly. So this is an image of one of those dwarf galaxies. Okay, so that's a very weird galaxy. So weird galaxies produce weird pulses. A few years later, nope, we found FRBs coming from all sorts of galaxies. Elliptical galaxies, spiral galaxies, dwarf galaxies, from different regions of galaxies and so on. So it was when we thought, okay, we are narrowing down the solution to something, newer FRB pulses produce newer problems. That's what happened. Yeah, by this point, there was an explosion in the ideas, the theories for what could be producing FRBs. There are so many theories that at some point there are more theories than the number of FRBs that we're seeing. To give you a sense of that. So, yeah, so that's actually an FRB theory catalog wiki website that contained an entire catalog of all the theories for FRBs. And in 2020, we actually had a big breakthrough. On 28th April 2020, we finally detected an FRB coming from our own galaxy for the very first time in 15 years since its discovery. It's extremely close, so we can point all our telescopes and find out what the engine of these FRBs are finally, right? And yes, the engine was actually found to be a young flaring magnetar. Magnetars are neutron stars, but these have 1,000 times stronger magnetic field strengths than the regular pulsars, an entirely different beast. So how do magnetars emit FRBs? The idea was that, okay, here's a cartoon. This is a cartoon of a magnetar, and the loops that you see here are the magnetic field lines on a magnetar. And we had an earthquake in the morning, 7 or something magnitude. Magnetars also have sort of magnetar quakes. And these magnetar quakes can launch magnetic flares from their surface. This is an artistic conception of a flare that's launched from a surface of a magnetar. And many such flares are usually thought to be launched from magnetar surface, and they collide against each other at some faraway distances. And these collisions can produce shocks. And I said earlier that in order to produce an FRB-like emission, you have to have a coherent emission mechanism, something like a laser. So where is the laser here, right? We don't have a laser, but we have what's called synchrotron masers. So what I'm going to talk about now here is just one proposed theory, but there are multiple other possibilities, including curvature radiation and so on. I'm not going to go into that. I'm just going to focus on one example of what could be a laser equivalent happening in magnetar shocks. So this is the shock. So the shock that you see here is what this is a cartoon of that shock. The red one is the shock material, and the shock is going to bombard the electrons and positrons and all these particles that are upstream, and they're going to energize these particles. So the electrons, what they do is they come and they orbit around the magnetic field lines, because magnetars have magnetic field lines. I showed the curve, the loops, right? They orbit around these magnetic field lines. They eventually lose their energy through some mechanisms. And all these electrons together, they coherently emit electromagnetic waves in radio band. That's one of the ideas. Do we know that it works? People have actually conducted first principles simulations of such shocks on supercomputers. So this is this is a result from one such simulation. Here I show the magnetic field. Here I show electric field, and the ripples that you see near the shock are actually waves of electromagnetic nature. So that's actually electromagnetic waves that is propagating ahead of the shock. Okay, so young magnetars that are maybe decades or century old can produce these flares that can launch FRBs. So is everything solved? Not really, because 1 year later, one of the FRB, one of the huge telescopes that detects lots of FRBs, it's called CHIMES in Canada, they released a catalog of these pulses. And what we saw was a remarkable difference between the repeating class of FRBs and the non-repeating class of FRBs. The repeaters, the non-repeaters that I show here, they are actually just a few milliseconds in duration. They're extremely short, whereas the repeaters, they're actually longer in duration, maybe tens of milliseconds. And the repeater, the pulses of the repeater show this drifting frequency substructures. The high frequency comes earlier, low frequency comes later. Mind you, this is not due to the dispersion measure that I showed earlier. Here, this pattern is actually due to the intrinsic nature of the source. The source is emitting an FRB in a sad trombone-like structure. That's the word that radio astronomers use to call. Yeah, that's a sad trombone to call these repeating pulses. So this is suggestive of more than just a single young magnetar-based engine to produce all the FRBs. All right. And another discovery that came soon around that time was periodicity. Among a few repeaters, a couple of these repeating sources were seen to be periodic, in the sense that this source 180916 was repeating its periodicity every 16 days. It remains active, it emits FRBs for 5 days, it turns off, and then it repeats, it emits FRBs again for 5 days in a 16-day cycle. And this FRB 12102, remember the first repeater? This did the same thing at a 157-day periodicity. It emitted FRBs for about 80 days or so, turned off for a while, and then emitted FRBs again for 80 days or so on a 160-day cycle. And we have not seen such long periodic activities from any magnetar. There are about 30 magnetars in our galaxy, and we have never seen such activity from any of these magnetars. Could there be any other source? I don't know. And another clue came from studying the host galaxies' properties of FRBs. This FRB 180916 was actually pinpointed to be coming from this portion of a galaxy. And when you zoom in this region, do you see this green little dot? Yeah, astronomers were able to pinpoint the location of this FRB using Hubble Space Telescope to this little green dot. And this green dot was found to be about 1,000 light years away from this dark patch. And this dark patch are called star-forming regions. This is where young magnetars are born. And young magnetars cannot remain young if they were to travel 1,000 light years away. They would be older and they would not be flaring and producing FRBs. So something else could already be there, not some older engine. And this FRB 20O and 20E was localized to this little globular cluster of stars. And globular clusters usually contain older stars, older cosmic objects. Again, indicative of older stellar populations, something like accreting black holes or neutron stars. These are older systems. So what are accreting engines? So take a black hole or a neutron star and put a normal star. This is a normal sun-like star. I've just colored it in blue color for, looks nice, next to it. And this star, and the black hole or the neutron star, it pulls matter from the nearby star and eats a lot of matter. It can only eat so much and at some rate. If the matter is flowing extremely fast, then the black hole is going to expel a lot of material in the form of winds and jets. So these are winds, and these collimated conical structures, that's what are jets. And there can be flares launched from the base of the jet, from close to the black hole, along the jet. That's what I've shown here in the red region here. And these shocks can also produce an FRB-like emission, synchrotron maser and so on. And you can ask the question, okay, what's giving rise to the periodicity? So these jets would not always point along one direction. These jets precess. These jets sometimes point along our line of sight, and then they go away, and then they come back at some other time. And as long as the jet is pointed along your line of sight, you would see FRBs like emission coming from them. And once they go out from your line of sight, you do not see them. So are we just making this theory out of thin air. Not really. They have actually seen such wobbling motion of radio jets from galactic accreting black holes. So these are the little blobs that are launched from black holes along these jets. And if you notice, if you squint your eyes and see the direction along which it's launched, it's not the same. It's moving. The direction is also changing. So that was one of the ideas that we put forward to explain the periodicities seen from FRBs. So FRBs are millisecond duration flashes, right? What we saw was from the same FRB 121102, the same repeater, a persistent, extremely bright radio source at the same location as that of the FRB. So is this an oddity? Not really. In 2022, a couple of years ago, the astronomers found another source, 190520b, which also had a persistent radio counterpart from the location of FRBs. And now we have a third source with a persistent radio counterpart. So we now have a sample, we now have a population. So this is not an oddity anymore. And the idea that we had was, so you have an accreting black hole, and like I said before, it can only take in matter at a certain rate, and then it's going to expel a lot of matter. And these matter that's expelled in the form of winds and jets, they're going to collide against what's called circumstellar medium, and then it's going to produce various shocks, and these shocks can energize particles at large scales, and that can persistently produce radio emission. And we called these sources, these huge structures, huge bubbles that are inflated by the wind from the black hole, as we call them hypernebulae. Okay, so what I've discussed so far, this is just a teaser to the entire mystery of fast radio bursts. We don't have time to go through all the new exciting results. As of 2024, I'm going to leave with this slide. As of 2024, we have observed more than 20,000 FRBs. Do all FRBs repeat? If we stare at the apparent non-repeaters for a really long time, would we see another FRB from that? We don't have an answer. It has turned out to be that way for some sources, but not for all the FRBs. Do they all come from the same cosmic engine? Do magnetars produce all FRBs? Or do we need multiple engines, like the accreting engine case that I showed, or some other engines to produce these different classes of FRBs? What about their timescales? Typically, FRBs are millisecond duration engines, right? They carry as much energy as our sun puts in 100 years within a millisecond. But we have also seen FRBs lasting just a microsecond, and some FRBs lasting hundreds of milliseconds. What does this tell us about the nature of the FRB? What is the event rate of different class of FRBs? How often do we receive FRBs here on Earth? There are estimates that say 10,000 per sky per day and so on, but we don't have an idea of different classes coming at different rates. On what gives rise to the different periodicities, I just gave our theory for what it is, and we don't have a proof for what's giving rise to these periodicities that we have seen in FRBs. And there's still a big project. There's still big projects going on to understand the properties of the galaxies that are emitting FRBs, and to understand FRBs by studying the galaxies. What can we learn about the host galaxies of FRBs? And like I said before, these FRBs are coming from extremely large distances, right? Billions and billions of light years. I think the current record holder is like 10 billion light years, or so 8 to 10 billion light years. So they traverse a huge swaths of our universe's composition. They can inform us about the composition of the universe and the structure of the universe and so on. And how can we use FRBs as probes to understand our place in this universe? And again, what's the emission mechanism? The synchrotron maser that I shared was just one idea, but there are multiple other ideas. And not a single mechanism is able to explain all the properties of the different populations of FRBs. And we don't know what surprises lie ahead. And yeah, so as we make some progress towards understanding the properties of FRBs, we observe newer FRBs with stranger properties that completely defy our understanding. That's been happening for the past decade or so. And not a single model, like I said before, can explain the entire population of FRBs. We are just scratching the surface of this entire phenomenon, and much more research is needed to understand them fully. Yeah, I leave it here and happy to take any questions and chat at the other part. Yeah, thank you.
All right. Thank you very much for a very informative talk, Navin, especially given that FRBs is still such rapidly developing, and it feels like there are even more questions than what we can answer at this point, right?
Yep.
Yeah, so we're gonna start the Q&A session. So for all the in-person questions, I will be repeating the questions so that our online audience can also hear. So any questions for Navin, given what we have just talked about?
What are the differences between quasars and FRBs?
Great question. So do you want to come a little bit to the stage? So what do you see as the differences between pulsars and FRBs?
Yeah, so pulsars, as we know them mostly, they are coming from our own galaxy. These are also produced by neutron stars. And the brightness or the luminosity of the pulsars is about 1 trillion times fainter than typical FRBs. That's the big difference. And the other differences include the duration of the pulses themselves. And pulsars, they are often periodic. They repeat at a particular frequency, and they can be used as even replacements for atomic clocks. They're extremely precise, but FRBs are not that precise. They are some of the repeaters, they're not even periodic. They just flare off, they just come at random times. So these are some of the differences between pulsars and FRBs.
Great. Question over there.
What about searches and detections of other ways?
Good question.
Would you like to repeat
the
the
question?
question?
The question is, have we seen any other electromagnetic counterpart in different wavelengths to FRBs? In 2020, we did see an FRB coming from our own backyard, our galactic magnetar. And this FRB, because it is extremely close, we were able to point X-ray telescopes also at them. And actually, we observed spikes in X-rays coming concurrently almost with the FRB. So these X-ray spikes were about 100,000 times brighter than the FRB, or more energetic than the FRB pulses themselves. But X-ray telescopes are not as sensitive as radio telescopes are. So we have not found any X-ray or optical counterparts to FRBs from outside our galaxy. We just don't have sensitive telescopes. But there have been many efforts to point X-ray telescope for a really long time at extragalactic FRBs. We just haven't seen anything.
And there's actually a quite relevant question from Gregory online asking, does the rate, frequency, or time lapse of FRBs seen or already detected differ by galaxy types? For example, spirals or ellipticals, or do we even know?
That's a great question. I think that's an open research problem. I don't think there is a conclusive evidence of different rates of FRBs coming from different galaxies. Although there are some hints of some FRBs coming from certain galaxies that prefer star formation and so on. But I think that's still an open question, and we cannot answer. I cannot answer more. Yeah, I cannot give a conclusive answer to that.
Oh, that's totally fine. And we probably have like all the open questions online and from the in-person audience. So keep them coming. Any other questions for Navin? Over there at the back.
Yeah. Sorry, what? The wow signal. I think this was seen a couple of decades ago. Voyager mission, I guess. I don't exactly know. This was interpreted as some extraterrestrial intelligence, but I don't know much more about that. And FRBs are, I don't think they are produced by aliens. Although there were some theories on light sails by aliens producing FRBs in the catalog. I don't think it has to do with aliens or extraterrestrial intelligence.
Great. Question over here.
So even a coherent beam is going to diverge as it travels through space, which means that for any given size telescope, you're not going to get very much signal. So we're still detecting stuff from way far away. Are the ones we're detecting way far away in different class of energies than the ones that are closer?
That's also a great question.
Would you like to repeat the question?
So these pulses that are produced, the question is that they should also diverge. So are we detecting different class of FRBs at different places? Is that your question? Okay. So what we think is that the emission that's producing FRBs, they are moving at extremely at speeds extremely close to the speed of light. So there are effects of special relativity that have to be taken into account. And one of the effect is called just beaming. So what it means is, if you are traveling extremely fast, then the opening angle at which the FRBs are emitted will be smaller for an observer that's not moving extremely fast. So because of this relativistic beaming, the opening angle effect that you're mentioning can be smaller for an observer sitting in a different rest frame. So it's all the same FRBs. It's also the same population of FRBs, but it is possible that different FRBs were produced by moving medium at different speeds, and we could infer the properties of FRBs. We could infer the source of the FRBs by analyzing the properties of these pulses and using some models again.
Navin, since you are more on the theoretical side, I'm going to have a very theoretical question for you from the online audience. So Y1 was asking, is there a theoretical estimate on what percentage of FRBs we have already observed versus what remains to be discovered?
No, I don't think so. That's we just do not have an idea of what engines produce FRBs. We have ideas for what the volumetric rate or the occurrence rate of magnetars are. We have an idea for what the volumetric rate of accreting engines are, but we do not have a proper rate for FRBs to associate them to the known sources. So I don't think yeah, I don't think we can answer that question either.
Great. And I saw there was another question.
How do you calibrate this?
Yeah,
Great. How do you calibrate distances? So you mentioned maybe dispersion measure,
right.
But if there are like other ways.
Yeah, dispersion measure is the main way through which radio astronomers infer the distance of the FRB engine of the FRB source. Yeah, that's when the different colors of light arrive at different times, even though they are emitted at the same time. And time delay gives us the distance estimate.
Yeah, and in your presentation, you also showed a picture of Arecibo telescope, right?
Yes.
Yeah. So Rai was asking, has the loss of Arecibo affected your studies of FRBs, or as a community studying FRBs?
Yeah, Arecibo was a huge radio telescope in Puerto Rico, and it collapsed a few years ago. And Arecibo played a huge role in the discovery and characterization of FRBs, and it's a huge loss to the community. There are other facilities that are very much like Arecibo. For example, there is a 500, it's called FAST, 500-meter aperture something telescope, I guess. It's in China, and it's also sort of embedded in the in the ground. But yeah, in the US, it's a big loss that we have lost Arecibo.
Yeah, that's a little bit too bad. Any other questions before we end the Q&A session? Right here.
Yeah.
You mentioned that there's a wide range of theories behind this. Do any of them involve looking at potential instabilities and accretion disks in very intense magnetic environments?
For emitting FRBs themselves?
Yeah. So
yeah. So the question, the question is, are there any theories involving instabilities in the accretion disk itself to emit FRBs? I don't think so. The one that involves an accretion disk is something that I just presented. So even in that case, accretion disk itself is not emitting FRBs, but the jet that is launched due to the accretion process is what we think could be emitting FRBs.
Yeah, perhaps that's also a good theory to propose now that given we have tens of thousands of FRB theories already existing. Yeah. All right, so I know there are probably more questions that I didn't get to call on, but Navin will also be here right after this event. So, he's not leaving and going anywhere until all the questions are answered. Yeah, so feel free to join us right after this event. But let's give another round of applause.
Thank you. Thank you.
All right, so before we wrap up the event, I'm also going to quickly introduce what's coming up next. So as I mentioned earlier, this is going to be our last event of 2024. But in the new year, we have quite a few events coming up, starting with public stargazing, both in January and February, in person at the Stanford Student Observatory. And we will also have a public lecture on the application of AI in astrophysical studies in early February. And that is going to be talking about how this kind of interdisciplinary work will benefit both communities in astro and in computer science. There will be more events scheduled as we move forward with the quarter, but there will be another big science fair on the Stanford campus on April 19th. It's called KIPAC and Friends Community Day. Join us if you want to play with all kinds of hands-on activities, do live experiments and demonstrations, and there will also be a series of mini science lectures, not only on astrophysics, but also in all related STEM departments. So it's going to be a big celebration. It's family and kids friendly, all free, and we hope to see you there. And if you want to keep up with what's new with KIPAC, we also encourage you to follow us on social media or sign up for our mailing list if you want to get notified whenever an event is scheduled. So thank you everyone for joining tonight. I wanted to just bring everyone back to the screen to say a goodbye. We will follow up with an email tomorrow to ask for your thoughts and opinion about this event, including what you might want to hear for public lectures in the future, so we can feature them in the upcoming quarters. And since this is our last time seeing all of you guys in 2024, I wanted to just express our sincere gratitude on behalf of KIPAC for all your engagement and participation, whether this is your first time here or you have already been following us for a few years. So really appreciate that, and we hope to see everyone again in 2025, and happy holidays.